Okay, let's get started. Good morning, everyone. Welcome to your second lecture of Advanced Fluid Mechanics. I want you to form into groups of two. Okay, pick your neighbor or someone you know, you don't know, whatever. Just form into groups of two. We're going to do this thing called, it's not a quiz. It's just, fun testing of knowledge from the previous lecture or the previous several lectures. We're going to be doing that a lot throughout this course. Whenever we've accumulated enough material that you can qualitatively describe or quantitatively. So we're going to have you form into groups of two. And I will randomly, I'm going to ask you a few questions on the board, on the projector. I'll give you like 3 minutes. Your group should think about those questions. And I will randomly pick a group per question to answer that question. OK? So form into groups of two. Already formed. Yeah, maybe. Yeah. OK. So two. OK, perfect. Two. OK. You all ready? All right. So you got 3 minutes. Actually, 1 minute. 1 minute. I changed my mind. You have 1 minute. So what is a fluid? What is fluid mechanics? What is the difference between a liquid and a gas? And what is a shear force? No. If you want to write it on paper. But I'm going to ask you, and then you're going to stand up and answer. Yeah, feel free to discuss it. No need to. If you want to write it, you can write it. But I'm going to ask you, and you're going to stand up and answer me live. All right. So I'm not going to ask you. All right. Time. OK. Question number 1. What is a fluid? You guys, Fanju and yeah. What's a fluid? OK. So you have a fluid, you put a shear force on it, and this is going to keep on moving. So let me follow up to that question. Then what would a solid do? Snap back when you remove the force. Excellent. OK. What is fluid mechanics?
Fluid mechanics is the study of forces and displacement of fluid.
OK. Or how fluids respond to forces and how they displace, etc. OK. What is the difference between a liquid and a gas?
Liquids, they are more closely packed.
Yes. Yeah. OK. And what is a shear force?
Yeah, sure. It's a tangential force. So basically,
Tangential to what? Yeah.
along the plane of the fluid or surface that it's.
Yeah. So we typically, in mechanics, we have to define surfaces, and forces act on these surfaces. And a force can act normally on a surface or tangentially. The tangential force is called a shear force. OK. All right. So let me test your undergraduate knowledge. So pressure, is it a force or not? OK. But it's does it have a direction though?
Yes, partially concept.
OK, so it doesn't have. So pressure is a scalar. We're going to talk about this later in a little bit. But pressure is a scalar that doesn't have any direction. Once you define a surface, be it that the surface may be a fluid surface or a solid surface, then the action of pressure results in a force on that surface. What is the direction of that force? Normal. Yes, always normal. OK. OK, great. So we're done with this right now. Let's go back to our lectures. All right. So last time, we left off with a bunch of definitions. What is fluid mechanics and the difference between liquids and gases? And I told you that this week we were going to talk about the continuum assumption. Okay. Before we get to the why we need a continuum assumption, oftentimes, or the purpose, anything we do in fluids is, say you have, a flow, a jet flow, and just a flow, and a device like this. You have, these streamlines. You have a recirculation here, recirculation there. Experimentally, to quantify this flow, it'd be nice to have a value of the velocity everywhere, value of the pressure. We left off last week talking about that. So ideally, we want to be able to define or find the velocity at an arbitrary point in space, okay? Arbitrary point in space, not just at a few select points. So that would be really cool, right? Imagine you have a full description of what we call the velocity field or the pressure field across all of space. So any point in this domain. Now, we're going to describe this point by defining a coordinate system. So let's say you put your, your origin, you put it over here. So you say this is the x-axis, and this is the y-axis. And then any point can be defined by the position vector, r, which is essentially the combination of these 2 points, x at x of point P and y of point P. Okay? Now, strictly speaking, can we do this? If fluids are a collection of molecules, okay, how can we define an arbitrary? What if I choose a point where there are no molecules? I mean, if we go down to the molecular level, these molecules are freely flowing next to each other. They're bumping into each other. There's a gap between them. What if you pick a point in that gap? So strictly speaking, we really cannot define properties arbitrarily pointwise. Okay, but then how do we reconciliate that contradiction, that we cannot define properties pointwise? However, we still want to be able to define quantities pointwise. That's why we need a continuum assumption. Okay? It turns out that when we say the velocity, the axial velocity at a point x, y, z, or the density, rho, at a point x, y, z, and notice I'm also introducing some nomenclature over here along the way, okay? Or the temperature at a point x, y, z, we can also write it at a point r. What we're really saying is that we're defining this value as an average property, okay, as an average property of all the molecules in some vicinity of point r. Okay? So let's say this is point P, given by the position vector r. So we have xp, yp, and zp. And I'm going to draw this in 2D for simplicity now. What we're really saying is that in some vicinity of this point, and I'm blowing things really, really high, okay? In some vicinity of this volume of length L, we're going to take the average properties of all the molecules that fall within this particular volume. Okay? But there's a limit to how big this volume is. If you take this volume really small, such that you're covering only one molecule, or you may end up in a gap between two molecules, you cannot define things. So let's talk about density, for example. We know that the density is, we say it's mass over volume, okay? Reality, we can define the density as the limit of a small volume, limit as delta V approaches some delta V star of a small mass of molecules, delta M, the mass of the molecules collected in this volume, delta V, okay, over delta V. So what I'm saying here is I'm going to pick a volume, delta V, and I'm going to calculate the mass of the molecules in that volume, okay? and then divide that mass by delta V, and that is going to give me the density. Now I'm going to change that volume. So as I change the volume, if I increase it, I'm going to collect more molecules. If I decrease it, I'm going to collect less molecules. Okay, but it turns out that there's a threshold for this volume delta V where you can actually get like near constant value for properties. In practice, what we observe, so let's say we're going to plot, this is the volume delta V, and this is the density, which is equal delta mass over delta V. And this is in a descriptive plot, can be applied for water, air, other gases, liquids. So this is rho. I'm plotting rho. Initially, if you pick a very, very small volume, that is the size, almost the size of a molecule, you may hit a molecule, you divide by delta V, it's in a small volume, you may get a weird value for the density. Okay, you may get a weird value for the density. Let's say we're doing this for water, okay? And we say that the density of water is 1,000, okay, so that's 1,000 kilograms per cubic meters, okay? So you start with a very small volume, you may end up here, you take a slightly larger volume, you may still get one molecule, but the volume has increased, or you may get two molecules, and the volume has increased. So what you're gonna get is something like this, okay? Now as you increase V, you're gonna get to a point where this is real stuff, this is true. We can do this in molecular simulations, we can show this. You get to a point like this, and then as you increase your volume, you get possibly something like this. Okay? Now, what is this limiting volume, this point here where we start getting near constant values for the density? That's actually our delta V star. Okay? That's our delta V star. We call this region microscopic uncertainty. And up to a certain volume, we really don't care about this particular volume over here. Then we get what we call macroscopic uncertainty. Macroscopic uncertainty. Now this delta V star for fluids at standard conditions is about 10 to the minus 9 millimeters. Okay, that's a pretty small volume. So when we, yes? Sorry, millimeters cube. Yes, sorry. Good catch. Yes.
So would you determine that using like statistical mechanics?
Yeah, possibly. Yeah. Now you're really not gonna worry about this, but this is to be rigorous when we say we're measuring velocity and pressure. So for example, computationally, when we are doing a simulation and we're saying we have the velocity field at every point, as long as the discrete point is a little bit larger than this volume, we can still do that. Otherwise, we have to go to, molecular dynamics or something a little bit more different. Okay.
So one more question.
Yeah.
Is this continuum approach similar to like looking at a material body approach? Do you know what I mean by that?
What do you mean material body?
Like, so like the way
material elements?
Yeah, like you would pick like a collection of atoms and then write the laws off that.
Yes. I mean, yeah. That's an interesting question. So what he's saying is, and we're going to talk about this a little bit later. You're trying to distinguish between material elements and like a Lagrangian perspective and an Eulerian perspective. Yes, so that applies to both. Your collection. I mean, you can track one single molecule. Okay, then you don't worry about the continuum assumption there. You're just tracking what happens to that molecule, but you're going to get a lot of trouble because a volume like this, for example, for air at standard conditions has about, 10 to the 7 molecules. Just this volume. So imagine you're simulating a room, that has billions of this volume, right? And how many trillions of molecules you're going to track is just, unfeasible, okay? Now I'm going to introduce a slightly better definition for what we can consider continuum. So as long as we're making this claim now, as long as all our control volumes that we're going to be defining later are about this size, then we can rationally and reasonably and scientifically justify claiming that the velocity field, the pressure field, the temperature, all fields are continuous. So you pick a point, and you can measure. You pick a point, you take a volume around that point that's about this size, and you can make a measurement, essentially, okay? Okay, now there's another approach that is slightly going to be more helpful. Do you have a question? Yeah.
Does that control volume differ based on the type of fluid or the type of molecule?
No, first, I mean, yeah, when you get to fluids at very low pressures, we're going to see there's another way to look at this continuum assumption. But yes, if you are so this is at standard conditions. So when you go to very high pressures, that volume can go down, right? Because you're packing more molecules at very low pressures, this volume has to go up, right? Because your molecules, you have less molecules, right? Or they're more spread apart. Okay, any other questions? Don't get all worked up about this. It's just a way to allow us to rigorously talk about velocity fields and densities, etc. Okay? Another approach is to look at characteristic scales in a system, rather than saying, I want to define an ultimate volume that's 10 to the minus 9 millimeters or whatever. Let's look at relative scales in a system. And I'll give you this analogy. It's not really an identical analogy, but just to give you the idea of how relative things matter. So let's say you're measuring a bridge, okay, that is 1 kilometer long, based on several measurements. You go and commit an error of 1 centimeter. Is that significant? No, because 1 centimeter relative to 1 kilometer is nothing. Okay? But let's say you're measuring a nanochannel that's 10 nanometers long, and you commit an error of 1 nanometer. That's a big deal. It's a 10% error. Okay? So if we look at relative scales in a system, we can also make a claim about the continuum assumption. Now, what if so what matters here is how closely packed these molecules are. So again, think of a fluid. I'm going to zoom in really high into this fluid. These are fluid molecules scattered around each other. And there is an average distance between these molecules. Does anyone know what that's called? Mean free path. So what is the mean free path? Yes, exactly. So let me say that again. He said that the mean free path is an average distance that a molecule has to travel before it bumps into another molecule. So that tells us that typically this is how far these molecules are spaced apart. Okay, so we're going to take a bunch of molecules and put them in a system. We're going to take water, for example, put it in a nanochannel. Okay, and what we can do is compare this spacing to a characteristic length in your system. So in the nanochannel could be the height of the channel. Okay, and let's call that other characteristic length. So we're going to take a characteristic length Let's call that L. This could be anything. I mean, you can. I know we used to get stuck on like why is the diameter in a pipe flow the most important quantity when you're doing like the Reynolds number, right? You can pick another quantity, but you're going to see that it's not going to be significant because the diameter is actually what controls what happens in your pipe. But maybe then if you're looking at turbulence, maybe the length of the diameter is going to be of the pipe is going to be important. So pick a characteristic length in your system, okay? And let's try to compare lambda and L, okay? So a comparison of lambda and L. So if we take the ratio of lambda over L, what dimensions does this ratio have? It's dimensionless, yes, unitless. And that's called the Knudsen number, okay? It's a measure of the relative distances in your system, okay? So what happens? We have 3 scenarios. What happens if the Knudsen number is much less than 1? Knudsen number is equal to 1. Knudsen number is much greater than 1. So in this case, lambda is much smaller than L. So what does that mean? So think of, we have a lot of molecules in our system, right? So relative to the spacing between the molecules, our system is pretty big. So do you think we feel we would be safe if we make a continuum assumption over here? Yes. 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 Because we have a lot of molecules. Okay? Continuum. Okay. And actually, these two here are going to be equivalent. What happens when the Knudsen number is 1 greater or equal to 1? That means that, pardon me? Yeah. Yeah. So lambda is greater than or equal to L. So that means you have like 1 molecule in your system, right? Or less. So no continuum. No continuum. It could be your any system. Take a planet, planetary atmosphere. Take Mars, for example. What would you say the Knudsen number is on Mars? Pretty low. Sorry, it's pretty high because it's rarefied, right? There's barely any molecules. Okay. Okay. So let me give you 2 examples, and I'll ask you once you're done writing, and I'll ask you if these systems are, we can make a continuum assumption or not. So the Knudsen number is nice because it gives you a rational measure. So when you go and when you're doing your research, you're investigating possibly biological flow in a channel under a microscope, and you're measuring flow rates or velocities. You want to make sure that your velocity field, you have a continuum so that you can do a velocity field description, okay? Or if you're developing a model for that flow. Okay, so I'm going to give you 2 examples. I'm going to take a, let's see, a nano channel. Nano channel. And I looked up these numbers. You can look them up on the internet, Wikipedia. You can, if you're struggling, you have a system and you're kind of confused, you have a big tank, low pressures, you have oxygen or air, go look up the mean free pass, get a characteristic length for your system, and then calculate the Knudsen number. If it's less than 1, you're good to go, okay, with it, making a continuum assumption. Yeah?
Mean free paths, determined for mixtures, are they different?
Yeah, I don't know how they do this measurement. There's certainly some statistical mechanics going on there, some molecular dynamics, some observations, but there's a lot of theory. If you go to the kinetic theory of gases, and yeah, I mean, you're going to see some of that in your later courses, at least be exposed to some topics related to that. Okay, so the nano channel, the length of my nano channel is 10 nanometers. And I'm going to put water in it, and it has, under the conditions I put this on, let's say it has a mean free path of 0.1 nanometers. Okay, so let's calculate so at face value, you'd think, wow, this is a pretty small channel, right? 10 nanometers. So we probably cannot make a continuum assumption. Actually, you can, because the Knudsen number, in this case, is lambda over L. That's 0.1 over 10. It's 0.01. Okay? You can rationally, yes?
This is a terrible question. Is there any kind of threshold for the Knudsen number where we can say continuum or not?
Less than 1. As long as it's less than 1, yeah. I mean, then you get into, like, if it's 0.9, 0.5, I would say you're pretty close to not being continuous, but you can reasonably make a continuum assumption there. Yeah. Yeah. Pick your characteristic length wisely. Okay? Or change slightly the conditions. I would say if you're less than 1, and the vast majority of systems you're going to be dealing with are going to be continuum. Okay? But this is a system you may deal with. Assume you are, you get hired by Stanley. That, if you're an outdoorsy person, you're familiar with the Stanley brand. They make these really good mugs. Actually, So I hate this mug. It's just I keep forgetting the. This is by a European brand called Bodom. I was a gift, and I should get rid of it, but because I always forget to close the lid, and I'm like grabbing it, getting out of the car, and just spills over, and people hear me blab in the parking lot. Like, what's wrong with that guy? But anyway, so this has a chamber, right? So you know how thermos work or mugs, right? There's this little kind of gap in here that has a vacuum, right? So is the air in the vacuum, is that a continuum or not? So let's take a thermos, for example, with air. So let's take the example of the thermos or mug. And lambda is 1 millimeter. And the gap is about, so the characteristic, what would be a good characteristic length is the gap. Doesn't matter how tall the mug is, it's actually the gap that matters. So in this case, it's 1 millimeter too. So what's the Knudsen number? It's 1. So no continuum. Yeah, and kind of any convective flow in it, right? So you cannot make. Yeah. Any questions? No continuum. Okay. Yes.
Choosing the characteristic length of the system. So you chose the gap between the two vacuums. But someone could have chosen the height of the mug.
But that's not a good choice, because how tall is the mug is not going to matter, because what we're worried about is, for example, the convective heat transfer between the inner wall and the outer wall. So the gap is what matters, and how many particles you have in there is going to affect your conductivity and convective heat transfer, right? So
We have to understand the system, how it's working.
yeah, you have to understand the system. Yeah, and if you're confused, take a couple of compare the two different length scales that you have in your system. All right. Okay. Yes. It depends on temperature and pressure. Yeah. Lambda is different for different gases and liquids and fluids and right. Yes. Yes. That's the reason why lambda is so large in this case compared to lambda in here. So it's there's two things going on here. The fluid itself you're dealing with, the fluid you're dealing with, water, is obviously going to have a smaller lambda than air or oxygen, but also what matters is the pressure and the temperature, etc. Okay? So gases are a little bit more sensitive, or much more sensitive to gases and temperature. Okay, great. Now, before we get into really fluid mechanics, I want to get some things out of the way, essentially review of math, specifically vector algebra and calculus and some tensor algebra. We're going to come back to tensor dyadics a little bit later when we need them, because they simplify things for us. But let me ask you this first. What is your background in vector calculus, vector algebra? So you know what a vector is, I'm assuming, right? You're familiar with dot products, cross products, familiar with gradients, divergence, curl. Not with the divergence and curl. Okay. So let's go ahead and review just to be thorough, just in case you have any gaps like I do in many things. So I like to review things. And this is actually good because it allows us to communicate using a standard nomenclature and language. Okay. So we are going to distinguish in this class between three quantities. So we start vector algebra plus calculus. So with algebra, we're going to talk about adding, multiplying, subtracting vectors. With calculus, we're going to be talking about derivatives and integrals of vector fields. Okay? So we're going to define between three things. We're going to distinguish between three things in this class. Scalar, and that's a single value quantity that doesn't have any direction or just a value. Okay? When we say the density at a point is 28 kilograms per cubic meter, that's the density at that point. Doesn't have a direction, doesn't make any sense for it to have a direction. Okay? So a value without direction. Then we're going to distinguish, we're going to talk about vectors. So what's a vector? It's a value of the direction, right? So value plus direction. And a tensor, what's a tensor? To be specific, tensor of rank 2. What's a tensor? Okay. So a lot of values. For the purposes of this class, we're going to be dealing with what we call tensors of rank 2, and they have 3 to the power 2 components. Okay, so that's 9 components. Think of it as just bookkeeping keeping of 9 related values. Okay, we will represent. Yes.
I got another bad question. So what's the difference between this and like a matrix? Is it just that it's the same?
So no, they're different. A matrix is a system of linear equations. It's a representation of a system of linear equations. We use matrix notation to describe tensors because it's just easier.
Yeah.
But it's not a matrix. I mean, you can call it. We call it. Oh, look at the matrix of the diffusion tensor. It's of the diffusion flux, for example. But it's technically a tensor. We just use a matrix notation because it's useful for it. But technically, a matrix is strictly a representation of a system of linear equations. Okay? Yeah, we just use the matrix notation for simplicity. So we're gonna use matrix notation, and we're gonna talk about this, something like this. Okay. Okay. Now, like I said, with the scalar, if you're in a random place in a fluid, you define for things that are scalars are density, temperature, pressure. Things that are vectors are velocities. Okay. Velocities, gradients of pressure. We're going to talk about that. Now, to make this possible, we need to define a coordinate system. So before you set up to solve any problem, you need to pick your origin and say whether you're going to be Cartesian or cylindrical or spherical. The vast majority of the time we're going to be dealing with Cartesian. So let's just go pick a coordinate system. And we're going to be dealing with right-handed orthogonal, orthonormal coordinate systems. Okay? So right-handed means you go from one coordinate to the other. You take your right hand from x to y, that's going to give you z. From y to z, it's going to give you x. And from z to x, it's going to give you y, as if you're opening a valve or something. Always actually use the right-hand rule to open a valve. Because think of it as like rotating and you're going up, right? If you rotate this way, you're going to go down. Okay? Now, all of these fields are going to be described. So the velocity vector, or let's start with density, is going to be described by x, y, z, and also t, because this system is changing in time. So that's our fourth dimension. Okay, so at every point, all of these quantities, we're going to describe them with x, y, z, and t, and also in equivalent notation, r, t, where r is the position vector of the point in question. Okay? Okay. Now, a vector is also a function of x, y, and z and t, or r, t. Because vectors in 3D have direction and magnitude, we can write them as a magnitude of the vector plus times the direction of the vectors, kind of redundant definition. Okay? So this notation here says we're just going to take the length of this vector. Okay? This thing here is going to give us the direction of the vector but it's a unit direction. So the magnitude of this thing is 1. So in other words, it's like this little unit vector over here. And if you think about it, you're taking the actual vector u and dividing it by its length. That gives you a length of 1. Now, the traditional way you've seen vectors written are, ux, uy, uz, 3 components in 3D. So if you think about it, and we're going to talk about the position vector here. So if you have a vector like this, vector A or vector u, it's going to have 3 components, x, y, and z. This is going to be uz, and this is going to be ux, and this is going to be uy. Okay? Now, I said that the velocity vector u, I'm saying velocity just to kind of fix that in your minds. So the velocity vector u, I said it's a function of space and time. What about its individual components? Are they also a function of space and time? Yes, absolutely. Absolutely. So ux is actually ux of x, y, z, and t. Uy is also uy of x, y, z, and t. And same for uz. Keep that in mind because it can be confusing. Because many think that, oh, the vector, this is ux, uy, z, so ux is only depends on x, uy only depends on y, and uz only depends on z. No. Ux is only the x component of the velocity field. Now, another way to think about it, forget about the velocity vector field. Because in the end, vectors make things easier. We can define the x velocity field as a scalar. Okay? You can define the x velocity field as a scalar. And you can define the y velocity field as a scalar. And the z velocity field as a scalar. Each one of those fields is no different than the density or the pressure. Each one of those doesn't have a direction. It's just the x velocity field, that's a scalar, right? When you combine them together, they make a vector. Because we understand that velocity, it makes sense because it has a direction. You can point this way or that way, right? So that's why we combine them together, makes things easier. But strictly speaking, each is just a collection of 3 scalar fields, each of which is a function of space and time. Okay, keep that in mind. Okay. Now the magnitude of a vector u is simply the Euclidean norm, or just like it's the generalization of the Pythagorean theorem. Okay, hypotenuse squared is equal to the sum of the 2 sides. The square root of that gives you the length. So the magnitude of a vector is simply the square root of the sum of the square of its components. Okay? Just a simple length. Okay? It's a generalization of the Pythagorean theorem. For n-dimensional vector fields, it's the same thing. Square root of the sum of all squares. Okay? So now, since we are dealing with orthonormal coordinate systems, the great thing, why do we define coordinate system? Why they are so useful? Because any vector defined in a 3D, in this case, can be expressed as a function of what we call 3 basis factors. So those are the unit vectors I, j, and k that you're familiar with. Okay? So I'm going to follow up on this, and we're going to take the coordinate system. Wow, I'm drawing perfect right angles today. X, y, and z. And we're going to put unit vectors. These are vectors that only have a direction, essentially, and they have a length of 1. Okay? We're going to put the unit vector. We call this I, and I put a hat on top of unit vectors. Okay? I or EX. So you're going to see both notations. Okay? And J or EY, and K or EZ. Okay? Whenever you see a hat, that's a unit vector. Right? Now, what are the components of each of the unit vectors? You know this, I, is given by 1, 0, 0. It has its length 1, right? And it doesn't have any components in the y and z directions. So it's 1, 0, 0. J is 0, 1, 0. And k is 0, 0, 1. Okay? Now, like I said, what's so cool about these orthogonal coordinate systems right-handed is that you can write any vector as a function of these basis vectors. So if we take our velocity vector field, which is made up of ux, uy, uz, we can write this as a linear combination of ux, ui, uz, and ijk. So what's a linear combination? It's just a combination of linear terms, okay? We're going to put uxi. So that tells us that u has ux in the I direction plus uyj plus uzk. Just a bunch of notations, okay? Okay. So you can get from this to this very easily because this is essentially ux times 1, 0, 0 plus uy times 0, 1, 0 plus uz times 0, 0, 1. And that gives you ux 0, 0, right? Plus 0 uy 0 plus 0, 0 uz, which is, you add them up, ux, uy, uz. Okay? Okay. Now, I'm also going to be using intermingling different, like we did the different notation for I and ex, ey, ez. For a velocity vector, we're going to also, sometimes you're going to see me write uvw or u1, u2, u3. Yeah? Use whichever notation you like. In all my writings, I like uvw. Don't want to worry about 2 and x1 and x3, just uvw. I'm simple that way. But you're going to see me intermingle all of these together, okay? All right. Now what I did here, I did something interesting, right? What did I do? So I had sum of one vector plus another vector plus another vector, and I added them. So that's vector addition, okay? That's the first element in vector algebra, is vector addition. You know you can add vectors, thankfully. So vector addition, vectors A and B can be added, and the resultant vector, we're going to call that C, is equal to AX plus BX, AY plus BY, and AZ plus BZ. You just add the components, okay? And A plus B is equal to B plus A. I know this is redundant, seems obvious, but actually there's this thing called non-commutative algebras where A plus B is not equal to B plus A. Use that in quantum mechanics and other things. Okay. Same thing, we can subtract vectors. So A minus B is simply, again, AX minus BX, AY minus BY, and AZ minus BZ. Okay? So the result is a vector. Okay? You add vectors, you get a vector. You subtract vectors, you get a vector. Okay? Multiplication by a scalar, alpha A, is simply a multiplication of rescaling of the individual components. Again, think of the position vector. You know, if the position vector is r111, and you say 2r, you're like 2 times away from that, but in the same direction as r. Okay? So that's alpha AX and alpha AY and alpha AZ. Okay. Now, what about the product? This is where things get a little bit complicated. Okay? Because addition was kind of obvious. You just add the individual parts, right? What about a product? Do you multiply the individual components of the product? What does that give you? And what does that even mean? So we're going to define two types of products. And why do we define those? Because we find them useful. They're just going to show up everywhere. So we go ahead and define them. There's nothing mysterious about it. Okay? I think, no, I have 5 more minutes. Okay. So I'm going to erase this stuff. We're going to start by talking about the scalar product. So what is another name for the scalar product? Yes, scalar or dot product. Okay. I was going to give you the definition, and then we're going to talk about what it means. Okay. If you have two vectors, A and B, the dot product is defined as an operation, and we're going to give this operation the symbol dot. Okay, that's how we write it. Not multiply, not star, A dot B, the symbol, the period symbol. And that's defined as the magnitude of A times the magnitude of B times cosine of the angle between A and B. So, in other words, if you had vector A and vector B, and this is the angle theta, the dot product is simply magnitude of theta magnitude of B times cosine theta. But what does that mean? This was beaten to us since whatever. Yeah. Okay. So if you project one on the other, if you want to project A on B, what is that? So the projection of A on B, let's say. So projection of A on B, what is that? It's this quantity, right? And that quantity is A cosine theta. So it's not quite the dot product. But it gives you the component of A in the direction of B. Okay? What if you project B on A? Projection of B on A, it's going to be B cosine theta, right? So that gives you the component of B in the direction of A. But somehow the school product combines the two together. Okay? So let's assume now that we do the projection of A on the unit vector in the direction of B. Okay, so let's take that unit vector in the direction of B and call it U. Okay? What is U? It's a unit vector. It's B over the magnitude of B. Correct? It's a unit vector. You agree that this is a unit vector. We just defined it. So let's take the projection of A on U. Okay, what is that? So A, the projection of A on U, projection of A on U, I'm going to use the dot because I know it's going to be the dot product, is simply A times cosine theta, correct? So you're partially right. The projection of A on B is actually the projection of A on the unit vector, okay, pointing in the direction of B. Okay? But now something cool happens. If you replace U by its value, B over B, gives you A cosine theta. This is still the component of A in the direction of B. But if you take B now, or you multiply by B everywhere, you get A dot B is A, is our dot product, times B times cosine theta. What that actually tells you is how much both vectors are pointing in the same direction. Okay? It tells you, so A cosine theta tells you how much A points in the direction of B. B cosine theta tells you how much B points in A. A times B times cosine theta gives you how much A and B point in the same direction. So if this is kind of the average direction for A and B, they're kind of tugging in both directions, you're pointing in that direction, how much are they pointing in that direction? So now that gives you two degenerate cases. If A and B are parallel, if A is parallel to B, A and then B, they're both pointing in the same direction, It's going to give you a, pardon me? Yes, so we're gonna get the maximum pull in that direction, okay? Now, what if A is perpendicular to B? Zero, right? Tariq said 0. That's right. So here, A dot B is simply A times B. I want you to think of this intuitively, okay? Here, A dot B is 0 because they're perpendicular. They don't share any direction, okay? So in other words, we're going to use this in the future to our advantage. We're going to say, okay, how can I find a quantity that's perpendicular to the vorticity? Or when is the vorticity perpendicular to the velocity, or tangential, okay? So we're going to use these to our advantage, okay? And component-wise, we can prove this next time. A dot B is simply AX BX plus AY BY plus AZ BZ. It's a scalar. It's a value. We took two vectors. When we added them, we resulted in a vector. The dot product is going to give us a value, a quantity, in no direction, no nothing. It just measures how much the two vectors point in each other, in the same direction. Okay. With that, we'll thank you for staying a couple more minutes, but